So now what we have done so far is we developed the model to understand how the temperature changes along x direction on a cooling fin. And we came up with an equation with some constants to be found, which is theta is equal to C1 sine hyperbolic lambda L psi plus C2 cosine hyperbolic minus lambda L psi. Now we're going to find out the C1 and C2. So we came up with theta is equal to C1 sine hyperbolic lambda L psi plus cosine hyperbolic minus lambda L psi. Okay. And okay, so I need to come up with boundary conditions. So what do I know? I know the first boundary condition, like here. If you think about this as the fin, right?
Sorry, are you missing C2?
Say it again.
Are you missing C2?
Yeah, I'm missing. Yeah. Thank you for correcting this. Okay, good. Okay, so already found data, but not C1 and C2. Okay. So need boundary conditions. Now we know one boundary condition, like at the wall, temperature is equal to T wall, right? And this basically corresponds to where x is equal to 0. So basically I know that at x is equal to 0, T is equal to T wall, right? And I can convert it into theta and psi, what theta is when psi is 0. But I don't know any other boundary conditions yet, but I can just come up with different cases to write down different boundary conditions. So for example, so let's see, what about a second boundary condition? Why do we need a second boundary condition? Because this is like, I need two unknown values to be found, C1 and C2, so I need two equations for that. That's why I need two boundary conditions. And this is most of the time is the case for second order ordinary differential equation. So for the second boundary condition, let's come up with different cases. Case 1, let's imagine that, suppose the end of the fin is insulated. What does it mean? I have insulation here. What does it mean? At x is equal to L, any idea? When you have an insulation, there's not going to be any heat flux across the insulation. And let's imagine that this is perfectly insulated. So there's no heat transfer along this direction crossing the insulation. So the, oops, yeah. So the Qx at x is equal to L is going to be 0, or in other words, from Fourier's law, you have this dt over dx, which is equal to 0. So that's another boundary condition. So when you have insulation at that surface, temperature across the insulation, the gradient of the temperature across the insulation is 0. dt over dx is 0. Okay, so I'm going to write this in a non-dimensional way. in dimensionless quantities, the first boundary conditions that I actually wrote down here at x is equal to 0 means psi is equal to 0. T is equal to TW means theta is equal to, we know that TW minus TF over TW minus TF, right? That's equal to 1. You have the same numerator and denominator. The boundary condition 2, as I told here, is at psi is equal to 1 because it's L over L. The derivative of the theta with respect to psi is going to be 0. There's going to be some unit conversion factors, but doesn't matter. I'm multiplying with 0, so it's going to be 0 at the end. So the theta over the psi is 0. Okay, so these are my two boundary conditions. So let's find C1 and C2 under the light of these boundary conditions. So using the C1, we get 1 is equal to C1 sine hyperbolic 0 plus C2 cosine hyperbolic 0. And we know that the sine hyperbolic 0 is 0 from here, and cosine hyperbolic 0 is 1. We found that C2 is equal to 1. Okay, we found the C2. Now, let's find the C1. Now, let's use boundary condition 2. Yeah. So I need to find out the theta over the psi first using this equation. C1 times the derivative of this sine hyperbolic is the derivative of the inner terms times the derivative of the sine hyperbolic, and inside the derivative of the whatever's inside is lambda L, and that's cosine hyperbolic. It's the derivative of sine hyperbolic, lambda L psi, plus C2 lambda L sine hyperbolic lambda L psi. And note that the derivative of the cosine hyperbolic is not the minus sine hyperbolic, unlike the trigonometric functions. The derivative of cosine hyperbolic is the plus sine hyperbolic.
Should you have an H after the sine?
Yeah, exactly. It's sine hyperbolic. Exactly. Thank you for the correction.
Wait, shouldn't it still be minus C2? Because on the cosine hyperbolic on the top equation, there's negative lambda.
Is it? Well, actually, that's a mistake because we, this is basically the, you already have the minus. Well, actually, for the cosine hyperbolic, plus and minus, it's an even function, so it doesn't matter. But I actually meant the plus there. Okay. All right, let's go back to our previous notes. Yeah, I mean, doesn't matter. You can actually think about it as plus 2. But here it's minus, definitely. The exponential minus, right? But for when you talk about the cosine hyperbolic, plus or minus doesn't matter. It's an even function. You can actually just play with the position of e to x and e to minus x. Does that make sense?
Yes, thank you.
No problem. But I meant actually positive, but for this case, it doesn't matter. Good. So from here, boundary condition 2. This is 0. Oops. And this one, I need to plug in here and here. Say 1, 1. Okay. So I get 0 is equal to C1 lambda L cosine hyperbolic lambda L plus C2 lambda L sine hyperbolic lambda L. And I already found that the C2 was 1, right? Okay. And we can solve for the C1, and C1 comes out to be equal to, after lambda and L's canceling, you get minus sine hyperbolic lambda L divided by cosine hyperbolic lambda L. And it's nothing but minus tangent hyperbolic lambda L. Okay. It's your C1. So let's actually wrap up and write down our theta, eventual theta with the C1 and C2 plugged in, minus tangent hyperbolic lambda L, sine hyperbolic lambda L psi, plus C2 is 1, so it's cosine hyperbolic lambda L psi. That's it. And you also write where psi is equal to x over L and theta is equal to T minus T wall, no, TF divided by T wall minus TF. So by knowing this equation, you can plug in x, find psi, and then plug in psi in this equation, find theta, and from theta you can find T. So you basically have the temperature profile in terms of dimensionless quantities. Okay. This is for thin end insulated. It's case 1, right? Okay, any questions so far? Yeah? Okay. What shall we do now? Now let's talk about another case, case 2. Well, actually, okay, let's talk about everything about the case 1 first. Now we found this theta for this case. Maybe we can come up with different situations and find the theta for different cases. But for this one, how can I find the heat loss? What about the heat loss rate? How can I find it? Now, there are two ways to find the amount of heat loss per unit time. One is the integral approach, and the other is the derivative approach. Okay. In the integral approach, you basically try to find out the heat loss summed over all the cross sections. Okay, so you can still think about this shell, right? And you can calculate how much heat is being lost, dissipated to the environment at each step, and you can actually take an integral and sum over all those shells, right? So you can say that the amount of heat loss is basically T minus Tx minus Tf times H times the area, which is the perimeter times delta x, let's call it P times delta x. But when you actually use integrals, the delta x's turns into dx's. And you take the integral from x is equal to 0 to x is equal to L. So that's the total amount of heat loss per unit time. Okay. You can do this, but it will take a lot of time to do it, like calculate this integral. But it's possible, and yeah, it's possible, and you can do it. Another method which you can do, and which is more which is easier than the integral approach, you can say, oh, whatever the heat lost there must be actually entering the fin at the wall. So you should say that if you think about the Q entering this region, Q enter, as the flux Qx at x is equal to 0 times the area, which is B times W, right, must be equal to the lost heat. Why? Because whatever enters should actually come out. So basically it's from in minus out plus generation is equal to accumulation. Steady state, no generation, and the in basically is Q dot enter minus the out is the Q dot lost, 0. So from here you can actually calculate the Q lost is nothing but whatever enters, which is basically this expression. So you can calculate from this expression. It's easier because you just take the integral. So let's estimate it. Qx. Let's find the Qx first. Qx is nothing but minus k dt over dx, right? And you can convert the dt over dx into d theta over the size by doing the following: d over dx over, oops, sorry. No, let's do it. I think this. Let's do it this way. D theta over d psi is d over d x over L. The theta is t minus tf over tw minus tf. From here, it's L over t minus tw minus tf times dt over dx. So from here, dt over dx is equal to tw minus tf over L, d theta over d psi. So you can actually plug this in here, and you find that it's minus k t wall minus tf divided by L times d theta over d psi. That's equal to, you can find d theta over d psi by actually taking the derivative of this thing, right? This entire equation, I mean. Let me write it down here. D theta over d psi is minus tangent hyperbolic lambda L is constant times the derivative of sine hyperbolic is cosine hyperbolic, and lambda L psi is lambda L cosine hyperbolic lambda L psi plus lambda L sine hyperbolic lambda L psi. And we should estimate that Psi is equal to 0. And you get basically, so this one is 0, this one is 1. So you have minus lambda L tangent hyperbolic lambda L. Okay. And yeah, I plug it in here. So this is psi is equal to 0. X is, I'm curious about the flux at x is equal to 0. Okay. So let's plug this thing in here, right? And then we get minus k tw minus tf over L. I have two minuses, let me call it plus lambda L tangent hyperbolic lambda L. There you go. Okay. So thus, that's the Q of x. The Q lost must be that Qx times Bw. So you have K times Tw minus Tf Bw divided by L lambda L tangent hyperbolic lambda L. Let's simplify a little bit. L's cancel, right? You can also plug in the lambda if you like, but you can just keep it like the yeah. Let's plug in. How about that? So let's say plugging in. We know that okay. So no, let's keep it like this. Q lost is equal to lambda k tw minus tf bw tangent hyperbolic lambda L. Good. You can check the units. This is 1 over length. This is length. They cancel.